Hello everyone, welcome to Physics Live with Ankan Bhattacharya once again. And it is known to you that I have started the new lecture series on numerical solution of ordinary differential equation, in which at the first lecture I have discussed some of the conditions involved in the solution of the ordinary differential equation, and the previous problem was given of first order and first degree. Here in this lecture I will going to show you about the second degree differential equations, second order differential equation solution by the numerical method. So what we have learned in the previous lecture about the initial value problem, and the first process to solve the initial value problem was the Euler's method. Now in this lecture I have planned to discuss the boundary value problem by shooting method. So the title of today's discussion is shooting method. Shooting method. Okay, let us try to understand the shooting method. So I have already told you that shooting method gets involved to sorry shooting method gets involved to some boundary value problem. Boundary value problem. Now what is boundary value problem? Let us try to understand this. Suppose you are given a problem dy dx is equal some f of xy, and it is known to you that at some point x0 the value of y is y0. So here the initial condition is x is equal x0, and at x0 the value of y becomes y0, and you are asked to solve the value of y at some other point. It may be at x1, or it may uh, or you may ask to solve the nature of y. What is the value of y as a function of x? This is known as the solution card for this differential equation. Okay, so what we are doing, what we were doing in the previous section is that according to initial value problem, the value of y at some x equal to initial point x0 given by y0, and some of the first order derivative to solve the second order derivative. Okay, I am going to tell you the thing which is some of the arrangement of PQR, that is the general equation of a second order differential equation is something like this. It is a general form of a second order differential linear differential equation, since the degree of the differential equation is 1 but the order of the differential equation is 2. So it is a linear second order differential equation, and it is of the general form. So for the solution according to the initial value problem, if it was treated by the initial value problem, then you should have the given value of y at position of x0 and y prime at position of x0 should be known to you. Suppose this is given to you, and you were asked to solve the differential equation on the basis of this initial condition. But if you are asked to solve the problem, the same problem, but you are given the value of y at some initial value, say y0, and another boundary value, suppose at x equal to xn, you are given value of y is yn, n may be 1 2 3 etc., and on the basis of these two conditions you are asked to solve the above differential equation, then the problem becomes some boundary value problem, as because the value of y at two boundaries are given to you, and you are asked to solve the differential equation on the basis of these boundary values. So it is a boundary value problem, and shooting method plays a dominant role for the solution of the boundary value problem. Now what is the shooting method actually? If I plot some y versus x, if this is the x-axis and this is the y-axis, and if the value of some initial point x0 is given to you y0, and the other value is at, suppose this value, this is the value of y at the other boundary, and at the other boundary suppose the value of x is x1. You have to approach this solution by guessing the value of y at this x1. Okay, so I have to shoot out the solution card that must end on this point. So I must take the value of the slope of this card so that the right slope will get involved to this, or the card may go from this to this, or the card may go from this to this. All of these cards approach to y1 but with different slope. If I get constant slope, then if I guess the slope of this curve, then either the curve will get approach to this point on the basis of the slope of the initial condition, or if the slope of the curve be chosen in such a way that it approaches to this point but not the actual point, then the choice of the slope will get wrong result. But by guessing we can calculate that how far I have chosen the point by guessing the slope. So according to this figure you can easily compare that the resultant solution that I obtained by choosing the guessing slope is something lower than the actual value. So it is known as the undershoot condition. We have shooted the solution but it is somehow less than the actual solution, as because the actual solution is known to you. Okay, so in this problem at x is equal x0 you are given y, the value of y is y0, and at x equal to 1 x1 you have the given value of y is y1. So you have to approach this so that you can get the resultant solution curve in this uh, plane, xy plane. Okay, and for getting the solution curve means to find out the solution of this resultant differential equation. So our main method is to guess the slope, and by guessing the slope, uh, the right choice of the slope will result the actual solution curve. We can approximately choose the slope by guessing these slopes, and by bisecting the slopes gives a more accurate result. And this is a great accuracy, as because the difference between the actual value and the value that obtained by solution is very small. So you can assume that the right solution curve is uh, obtained from your solution. Okay, you can say like this. But uh, if the value of the shooting procedure that obtain the value of y is somehow larger than the actual value, then it is will said to be overshoot condition, and the previous one was undershoot condition. Okay, so what I am telling to you is nothing but the basis on which the actual solution procedure will go on. So uh, let us try to put some numbers of the algorithmic step that gets involved to solution of the shooting method. Okay, let at first pick up some differential equation like this: dy dx. um, Let us say this is a function of x, y. Or more precisely you can say, you can pick up the general differential equation either, or you can assume like this. Let us suppose the given problem is to solve d2y dx2 is x square. So at first you have to break up this second order equation into two linear first order differential equation, so as to solve the second order differential equation becomes easier to you. So how can we break this second order differential equation? into two first order differential equation. Let us try to understand this. Let us suppose that dy dx is equal z. Okay, and let us suppose also this is a function of x y z, some f1. Okay, now our problem is d2y dx2. So dz dx means this, which is nothing but x square, which can also say f2 as a function of x y z. So as I am going to discuss the general procedure, so in general you can say that dy dx is equal sum f1 xyz and d2y dx2 is sum f2 xyz. This is the general condition, and it is a special problem. All of the problems can be reduced to these two sets of differential equation. Any second order differential equation can be converted to these two steps differential equation. Okay, uh, it must be taken to some first order differential equation like this dz dx. We will no longer use this d2y dx2, as because we have already considered the dy dx to be equal to z. Okay, so to find the actual slope you have to determine the value of z, that is dy dx, of the solution curve. For this purpose we have to guess the initial slope so that a curve can be drawn, but the curve may or may not meet the actual solution point that is given to your question. So by iterative method, by repeating iterative method, iterative means the repetition of the procedure that you are doing. So by iterative method, at last you can obtain the actual solution point, and if you are able to join the initial 2 points by some curve, by some slopes, then the curve obtained by obtaining the correct slope is known as the solution curve. And by approaching the solution curve, you can easily get what is the dependency of y over x. Okay, so this is our main motive, and let us point out the algorithmic steps which gets involved for doing this procedure. Okay, so put some heading, algorithmic step. Okay, I have to write it in white. Okay, algorithmic steps involved. Okay, so what I am saying to you, that at some initial value x0, the value of y is given to you, which is y0, it is given to you, and at some value of x0 you can calculate the slope. Z means the dy dx, z means the dy dx, z means the dy dx. Okay, so guess the slope as z1. This is the first guess. Okay, and by the solution of these two differential equation, the two differential equation is obtained by, you can solve these two differential equation either by rk2, either by rk2 or Euler method, or rk4, which I have already discussed. um, and here in the programming I will also show you by the help of Python program to solve this differential equation by shooting method, but I will not going into the details of the programming of Euler method or rk2 rk4. I will simply use a module of SciPy ODE. ODE is the module of the SciPy which can easily calculate the actual solution of the differential equation without writing any program. It is an inbuilt program present in the SciPy module. Okay, so it is the first step. We have the given point x is equal x0, given y is y0, and we have to choose first guess point slope z1 at some initial point x0. Next, the thing is the value of y at x0 is given to you y0, and the second guess will be Z2. This is the second guess. Okay, and the third guess will be obtained by interpolation formula, which is also a numerical procedure to get the solution of a algebraic equation. So the third guess can be formed by the second method or Lagrangian interpolation method, which must be equal to Z2 plus Z2 minus Z1 into Y1 minus Z2, sorry, Y1 minus, let us write in a fresh, Y1 minus W2. What is W2? I will get you to know W1. Okay. What is the value of Y2? Sorry. What is the value of W1? W1 is the actual solution of the differential equation as obtained by choosing the first guess point Z1. Okay. And W2 is the second solution of the differential equation as we choose the second guess point Z is equal to Z2. So the third guess point can easily be calculated by the second method or the Lagrangian interpolation formula. Z3 is equal Z2 plus Z1, and the Z4 can also obtain by Z4 is equal Z3 plus of Z3 minus Z2 into Y2 minus uh, W3 divided by W3 minus W2, and so on. So it is the iteration formula. So what we can do in the Python program, uh, we will do in the Python program to iterate the number 3 steps over a loop until the accuracy is achieved. Until accuracy is achieved. Accuracy is achieved means you have the correct slope to get the correct result, this by choosing the correct guess. As soon as you are not able to obtain the value of correct slope, you have to iterate this loop. I will show you with the help of simple program to solve this equation. So at first I will pick up a simple mathematical problem, simple algebraic problem to solve, and next the thing is I will going to show you how the quantum mechanical problem or quantum mechanical equation can also be solved with the help of this shooting method easily. So let us pick an example, mathematical example. Okay, please hold on. Yes. Let us pick a mathematical problem which we have to solve. So it is given to you. Problem. So problem. Suppose you are asked to solve y double prime is equal minus y plus 2y prime square divided by y, where you are given the domain of x ranging from -1 to 1, and at two boundaries -1 and 1 you are given the value of y to be equal to 1 by e plus e to the power -1. By calculating the value of this, you can easily get that this is nothing but 0.3243 dot 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 and so on. Okay, so the thing is, if we show by a graphical method, this is x equal to -1, this is x equal to 1. Here the value of y is 0.32 approximately. Here also the value of y is 0.32. Okay, so you have to find out the solution, that is the chord joining the 2 points. How this can be achieved with the help of programming, let us show you. Okay, for this I must have to open my Python notebook. Please hold on for some time. Yes. So let's start. So the name of the problem is shooting method. Okay. So let us call our module, import numpy as np. Next, I have to use the module ODE for the solution of the two differential equation, as because I am not wanting to long the program. I want to shortly describe the solution procedure, so I will use the module. Okay, so from scipy dot integrate import ODE. Okay, next we have to define the functions. So define f u x y z is equal nothing but u. Okay, and the first function and second function is, first means f1 is dy dx, dy dx is z, and the second one is d2y x2 means dz dx, so which is nothing but d2y dx2 means minus y plus 2y prime square, this means z, so minus y plus 2z square divided by y. So okay, let us put it here. Okay, so z, and which was minus y plus minus y plus 2 z square plus 2 z 2 z square divided by 1. Okay. So the two functions have already defined and return f1 f. So by recalling the function fux, it will uh, go to recall f1 and f2 this way. So x, next the thing is we have to discretize our domain x in the range of the boundary given to the question, that minus 1 to 1. X is divided, x should be divided within minus 1 to 1. Minus 1 and 1 are two boundaries. So in p dot lin space minus 1 to 1, and the number of division, let us say 101. Okay, next we have to define the initial value y, which is given to you in the question, that y0, the initial value of y is 1 by e plus e inverse. So let us say this is 1 divided by np dot e plus np dot e inverse. So it means 1 by this, put it in the bracket like this. So I have defined the initial value of y. Next you can say that y1, which is also the another endpoint, the initial value and the final boundary value is same given to you in the question, so you can write y1 is nothing but y0. Okay, next we have to pick the guess, two guess roots or two guess slopes, z1 and z2, which are very close together. So let us suppose that z1 is 0.1 and z2 is 0.3. Next I have to define u, which is, now if 1 becomes y0, so if 1 becomes y0 and if 2 becomes z1, so value of u is defined. Now solution is obtained by solving the problem keeping f, u and x. By the use of the module ODE, it is easy to obtain the solution for this case. Let us suppose the solution obtained is W1. So W1 is the solution of this. The total solution is given by up to this, but I am worried about the first solution only, that is only this solution for y equal to -1, let us say. Only this solution, I am interested to this one, the initial boundary. So for the first term I must have to write -1. Sorry. So now I should have to give the tolerance, which is say 0.001. This is the maximum deviation from the obtained solution to the actual solution. Okay, and I have to run the for loop for the next guess value. So for I in range, suppose up to 1000, the for loop will run, providing u is equal some y0 set 2. Okay, and the solution will also get obtained by gradient of f u x this, and w2 is the next solution obtained by the next guess root z2. So w2 will be solution, and this will get total solution, this will get total solution, but I am interested only to the boundary value. So this, and the for loop will run up to the difference between the two solution should be less than the tolerance. This. Okay, so z1 now becomes, by running the first loop, z1 z2 turns out to be z2 and z3 means I have write it already, z3 means z2 plus of z2 this. So I am no longer write z3, I will simply write the value or expression of the z3. So z3 is z2 plus z2 minus z1, and which must be multiplied by y1 minus w2 divided by w2 minus w1, and now I want w1 should be merged with w2. This will end up the for loop. Now I want to show you the solution obtained by the above numerical method, applying the above numerical method, and the actual solution given by the analytical method in the same graph. So for graph we must have to recall the another module. This. Okay, so let us plot the solution the total solution I want. So -1 is not taken here, as I want the total solution obtained by the above process and want to show it by this symbol. This, let us say, and let us plot the actual solution like this. The actual solution is nothing but given by analytical method like this, 1 by this. Okay, so I want to plot it in a dotted card like this. Next, the thing I have to show pt dot show. Okay, let us so let run the program. What is wrong with it? I think some error is happening here. ODE cannot be find out. Okay, let's check. Mm, what is wrong with it? Okay, the spelling is wrong. So s- here also. Yes, I think now this is right. Yes, here I am able to obtain the solution. So you can see it by zooming that the dotted curve represent the solution obtained by the numerical process above, and the orange color dotted curve, let us represent it in the this line. So the orange colored continuous curve represent the analytical solution, and the dotted curve represent the numerical solution obtained by solving it with the help of ODE. Now you can easily see that the two solution curve merged together. So we can say that we are able to obtain the correct solution for the above problem. So this is the main purpose of the shooting method, where we have considered the initial point this and guessing the slope of this curve, we are able to obtain the final solution and by solution curve. Okay, this is the main principle for the shooting method. Now we must have to apply it in our practical purpose for solving various problem in our physics. So let us discuss how it can be useful to obtain the solution in our physical problem. So it is tremendous useful for solving the Schrodinger equation. Why? Let us try to discuss it. So application of the shooting method in quantum mechanics. So now I am going to apply this shooting method to solve the Schrodinger equation, which is a fundamental equation of motion for the quantum mechanics. You can compare it with the Newton's second law of motion in classical mechanics, and it is also the fundamental equation for quantum mechanics. So the Schrodinger equation is nothing but minus h9 square by 2m uh, del 2 psi del x2 for one dimension v psi is some I h9 del psi del t, and you can easily obtain by applying the partial differential equation formulation and variable separation method. You can get the time independent part to be equal to minus h9 square by 2m d2 psi dx2 plus v psi is equal to some e psi, where e is the energy eigenvalue and psi is the energy eigenfunction. So let us remodelize the above equation so that I can solve it in a simple way. Sorry. So after rearranging this, d2 psi dx2 can be left in the left hand side, and all the term can be taken at the right hand side like this, and this is e minus vx psi. Okay, so now you can compare this equation sorry, I'm so sorry, today my health condition is not so good. I'm very much sorry to you uh, for interrupting, but I am helpless. Okay, so this was the number one equation, which gets modified to time independent part in equation 2, which also gets modified by rearranging in the equation 3. Now the equation 3 can be easily comparable to the general formation like this, here equal to sign was present. So general formation like this. So you can also separate these into two condition, and by considering psi to be equivalent to y, you can say d psi dx means dy dx can be taken to be equal to z, which is also a function of x y z. You can say like this, and d2y dx2 means d2 psi dx2, which is nothing but dz dx means vx minus e into y, which can also be taken to be a function of this. Now here I have chosen a scaling. This term 2m by h9 square is hampering here, and in quantum mechanics these have so small values, but should not be negligible in the quantum mechanics for the analytical solution. But when we use the solution to obtain from the computer, it is difficult for the computer to run the program by choosing these extremely small values. So it will take a long time. To reduce the time, To obtain the solution quickly, we must have to apply some scaling. Here I am applying the scaling to m by each line square taken to be equal to 1. This is equal to 1. This scaling I have used for this solution. Okay, so this is the first function, this is the second function. Now here it should be known to you that energy eigenvalue is constant, but here the potential is varying from the system to system. It depends on the system or model that we used. So let us pick up the simple model, that is a infinite square potential or one dimensional box potential, where the potential inside the box, let us draw. These are two boundary, suppose 0 to a, and the particle is trapped here, and inside the box the potential is 0 and outside the potential is infinite. This was the infinite square well potential that we have already learned in our theory lectures on quantum mechanics. But here I am going to solve this problem by the help of numerical method. So here it is known to you that inside the box the solution is more important. Outside the box the wave function will be 0, and wave function, as because there is no any probability for penetrating the particle throughout this wall, as because the potential is infinite. If the potential was finite, then the particle have some small probability, but have some probability to penetrate the boundary by the process of tunneling. So here the tunneling is not possible since the potential is infinitely deep box. Okay, so for this case the energy eigenvalue for this model will be nothing but En pi square h line square by 2m a square into some n square. Okay, but I have already but I have already sorry but I have already chosen the scaling 2m by h line square equal to 1. So choosing this 2m by h line square becomes 1, and we get the defined energy eigenvalue to be n square pi square divided by a square. Let us also specify our problem so that the solution gets easier, that the width of the potential box to be unity. Let us imagine that the width of the potential box is unity, so this should be 1, so it becomes n square pi square only, and the ground state where n is 1 2 3, it should not be 0. Energy means kinetic potential energy of the particle becomes 0, which is not possible from the uncertainty principle. All the things uh, you are known to all the things about it. So the n starts from 1, and for n equal to 1, the energy obtained is known as the ground state energy, which is nothing but pi square for this model, and it has the simple value 9.87, arbitrary unit, as because I have not specified the unit of A, I have not specified the unit of H line, so it is some arbitrary unit I can say. So the dependency with this is n square pi square. This is the dependency of the energy eigenvalue for the n. So the second energy, that is the first excited energy, will be 2 square pi square, means 4 into pi square, means 39.87 8. This is the first excited state. First excited state. Now I am worried about the wave functions, about the nature of the wave functions. But here it is the beneficial to us. It is beneficial to us that here the energy value is given. In case of quantum mechanics, the shooting method is beneficial as because the energy value is given to you, and it will also guide you to obtain the solution of the problem. But it is a boundary value problem, since according to the postulates of quantum mechanics, it is known to you that at the two boundaries of the given potential, the potential, sorry, of the given potential, the wave function